Hello and welcome to a video on solving trig equations. So we're going to be figuring out how to solve an equation that involves trig, where we're trying to figure out what, variable within a certain interval is going to solve these equations that involve trig. I know, crazy. We'll start off with the warm-up. You should pause the video and you should try it yourself. But you're just factoring with basically trig to see if you can figure out how to do that. You might want to use u substitution. So like this first one, I can see there's a cosine in both of them. So I'm just going to factor out a cosine. Now that's nice and factored. This one's a little trickier. I think a lot of you might benefit from treating it like u substitution, and then you could just do your normal factoring method, whichever way you want. So if we're using the AC method, we're gonna end up doing something like, I don't know, that, I think. And so we'll get 2u, u plus 1 minus a u plus 1. So 2u minus 1, and then u plus 1. And then we just resubstitute back in, right? So 2 sine x minus 1 and sine x plus 1. And so that would be fully factored. For the second one, you're just solving. So remember, when we are solving, we're almost always setting it equal to 0, factoring and solving. So for this one, we would move the u over, factor a u out, and then we would be able to say, hey, u is going to equal 0 and u is going to equal 1. Over here, same idea. We'll get 2u squared plus u minus 1 equals 0. That's going to end up factoring to 2u minus 1 and u plus 1. And while I did do that mainly in my head, I hope you kind of recognized that these guys are the same exact factoring that's happening up here, which is essentially how you would treat solving with trig functions. You could use a little u substitution to help you see it a little bit better, but essentially what we would do is say, hey, cosine x is going to equal 0 and cosine x is going to equal 1, and then we would have to figure out how to go from there. Same idea for letter B. So that's kind of the goal of what we're doing today. I'm just going to remind you of some of the things that are useful for us. So you should know your special right triangles, so that if you get like sine x equals 1/2, that you know that that's coming from a 30, and then you just have to figure out what quadrants it might be in. The quadrantal angles are particularly useful, because if you have, like, for example, that one where we just had cosine x equals 0, so we would have to say, oh, okay, when would cosine equal 0? It's going to equal 0 at pi over 2, and then again at 3 pi over 2, and things like that. So being familiar with these is going to help you out immensely when we're trying to figure out how to do this kind of basic solving stuff. So example 3 is going to literally connect those two warm-ups just like I was doing. So if we're trying to solve this, we're going to get them on one side of the equation. So I'm just going to subtract that cosine to the other side. If you can recognize how to factor this without using u, then that would be preferred. So I see that there's a cosine in both of those, so I'm going to factor it out just like we did in the first warm-up. And then I'm going to set each of those factors equal to 0, just like I did with the u's in the second warm-up. So I'm going to get cosine x equals 0 and cosine x equals 1. And then I need to think about what's happening here. So I know that cosine is the x values. And so if it equals 0 or 1, those aren't coming from triangles. Those are going to come from quadrantal angles. And so the x value at 0 degrees or 0 radians is going to be 1, so that can't be right. But when I'm up here, the x value, 0, 1 is 0, and when I'm way down here, which is 0, negative 1, that's also going to be 0. So for this one, paying attention to the fact that I'm only going one time around the circle, okay? So if I only want angles that are between 0 and 2 pi, so I'm not taking anything that's coterminal, I'm not going negative, none of that stuff, then I get that the answers to this first part are going to be x equals pi over 2 and 3 pi over 2. And those are the angles to get to here and to get all the way around to here. And then I just repeat this over here and I say, oh, okay, cosine equals x. all right, x is going to equal 1 when I'm right here, right? This is 1 comma 0. It does not equal 1 when I'm over here, though, because it would equal negative 1 if I was over there. So that's not going to be part of my answer set. But I am going to get that x equals 0 radians. And so these would be the 3 answers to this question. So pi over 2, 3 pi over 2, and 0 would all solve the equation cosine squared x equals cosine x. We're going to do the exact same thing over here. So I'm going to do exactly like we did up above in the warm-ups. I'm going to subtract the 1. I'm going to factor it. So if you need to use the full AC method, go for it. I'm going to not do that and hopefully not mess it up. I don't think I did. Set each factor equal to 0, so that's going to give me sine x equals 1/2. This one's going to give me sine x equals negative 1. And now I just need to think about where these things are happening. So 1/2, and it's positive, so I know that that's going to happen in quadrants 1 and quadrants 2, because remember, all students take classes. Sine is positive in quadrants 1 and 2, so I know that my answer has to be somewhere in quadrants 1 and 2. And then I have to think about what triangle would make this happen. So if I were to label this, you should hopefully recognize by now that this is going to be a 30, but I need to answer in radians. So a 30 in quadrant 1 is going to be pi over 6, and a 30 in quadrant 2 is going to be 5 pi over 6. So those would be the answers for that particular one. You do the same exact idea over here like we did in part A. I'm looking for when sine x is equal to negative 1, and I know that sine is y values. So I'm looking for when the y values of the quadrantal angles would equal negative 1, which is going to be down here. So I'm going to include 3 pi over 2 as part of my answer set then. So these would be the values of x. That would solve the equation 2 sine squared x plus sine x equals 1. Okay, so we're kind of combining all the stuff that we did in the basic trig where we were figuring out how to evaluate what sine of 30, cosine, tan of any of these things were. We're working backwards now. So we're saying, here's what the answer is. Where did this come from? Okay, so that's kind of what's happening here. It can get more complex as the equation gets more complex. So we'll do 4 and 5, and you'll kind of see what I'm talking about. And we just have to remember some of our main rules of solving. And one of the first ones is that you're never supposed to divide by a variable. Okay, so I don't want to do any sort of weird division here. I'm going to actually move the cotangent to the other side of the equation. So I'm just going to subtract it, get it equal to 0. That's one of our main things. And then I don't see anything obviously that factors right away. So we're going to go back to our simplifying strategies, and one of those was to turn everything into sines and cosines. So a cotangent is going to be a cosine over a sine. And now I can see a little bit of some stuff that's happening here. So I see they both have a cosine, and they both actually have a sine. So I can actually factor out a cosine x over sine x. And what I'll be left with is a cosine squared x minus 1. Okay, so I got rid of the fractions by factoring out the sine, and then reduced the top with 1 cosine there by factoring that out. And now we can do some more simplifying here because this looks vaguely familiar to me, and I think it's one of the identities that I'm supposed to know. And since it's involving a cosine squared and a 1, I'm going to go to our basic one, which is sine squared plus cosine squared equals 1. And I'm going to try to recreate this somehow. So I need a cosine squared x minus 1, so I'm going to subtract this 1 to the other side and move this sine squared to the other side. That's going to give me cosine squared x minus 1 equals a negative sine squared x. So I can actually replace this with a negative sine squared x by using our identities. So now I have cosine x over sine x times a negative sine squared x equals 0. And at this point, I'm going to set each of these factors equal to 0 so that we can see what's going on with it and actually try to solve these things. So in the first one, we're going to have to use some of our knowledge of fractions. So remember that fractions only equal 0 when the top of the fraction equals 0. So I can actually take this and just reduce it to say, when does cosine x equal 0? And then say, okay, cosine is x values. When do the x values equal 0? They're going to equal 0 here and here. So that's at pi over 2 and 3 pi over 2. And so I've now solved that one. For this one over here, I'm going to do the same exact idea. So I'm going to first divide by -1. That's going to give me sine squared x equals 0. Then I'm going to square root, which gives me sine x equals plus or minus 0, aka just 0. And then I can solve and say, okay, sine is the y values. Y values are going to equal 0 at 0 and pi. But we have a giant issue that's happening here, which is we're working with fractions, and fractions are one of the few things that we know of that have domain restrictions. So we have to actually pay attention to this. And if we're looking over there, we have a sine x in the bottom, which means that it cannot equal 0 because the bottom of fractions cannot equal 0. So if we had done this first, we actually would have recognized that this whole part is not going to be possible because we literally have that the domain says sine can equal 0. And all of that stuff I just crossed off was literally saying sine equals 0. But if we had wanted to establish the domain of this first, we would have basically just solved this and said, okay, when does sine x equal 0? It's going to be when the y values equal 0, which is going to be at 0 and pi. So x is not going to be able to equal 0 or pi in the interval 0 to 2 pi. And so I cross those answers out, and my only answers are going to be that x equals pi over 2 and 3 pi over 2. So we still have to pay attention to domain restrictions, and we have to be extra careful because this part you're not going to like, so I'm sorry in advance here. Let me get a good color here. You have to pay attention because tangent is technically a fraction, cotan is technically a fraction, cosecant is technically a fraction, and secant is technically a fraction. So for tangent and secant, they both have cosine on the bottom. So cosine x would not be able to equal 0 as part of domain restrictions if you have a tangent or a secant in a problem. And then cotan and cosecant, they both have sine in the bottom. So you would not be able to let sine equal 0 if you had a tangent, a cotangent or a cosecant in a problem. So it's actually useful to start writing the domain right away at the start of a question instead of kind of waiting at the end as an afterthought, which is what we used to do back in rational functions anyway. So we just have to kind of remember that some of these trig functions are going to act very similar to rational functions when we're working with them. So for example, in number 5, it says find all the solutions from 0 to 2 pi, so the same thing we've been doing. Let's solve this equation. Secant x plus 1 equals tan x. So I'm just going to rewrite that over here because that's where I'm going to be working with it. And I'm going to, off to the side, just immediately identify some domain issues I have. Okay, so a secant is really 1 over cosine. So I know that cosine x is not going to be able to equal 0 because that's going to violate the domain for the secant part, and then tangent is sine over cosine, so I end up getting the same thing, that cosine x can equal 0. I need to figure out when that is, so cosine is x values. X is going to equal 0 when I'm at pi over 2 and 3 pi over 2. So I'm going to get that my domain restrictions from 0 to 2 pi are going to be that x cannot equal pi over 2 or 3 pi over 2. All right, so now we have to try to solve this. And there's like a lot of different ways we could go about doing this, okay? So first thing you notice is that they're not the same. So when we're trying to solve these, we really want there to be like the same trig function. So if I go back to question 3, you notice how they were all cosines, all sines. So it's kind of annoying that they're not, and we want to try to work on that. One strategy we could try to do is turn everything into sine and cosine, like we normally like to do. So I'm going to write that down super quick, but I'm going to erase it, so I don't necessarily want you to write that down. So if I have 1 over cosine, which is what secant is, plus 1 equals sine over cosine, which is what tan is, I'm still going to end up having sines and cosines, so 2 different ones. And we don't really like that. It's hard to work with to try to figure out how to factor when they're not the same. Like, how are you going to factor something out if they don't have the same pieces? So we're going to try a different strategy altogether. And honestly, this strategy comes from uh, experience and recognizing things. So let me tell you what I'm recognizing here so that you can kind of get where my brain's at. So I'm looking at this, and I say, hey, I think I have an identity that involves secants and tangents. So if I go look at my identities, and I can go, oh, there's one right here. 1 plus tan squared equals secant squared. So it would be really cool if I had these things squared then when I'm over here. Because if they were squared, I would be able to use that identity, which was tan squared, I'm going to use theta, plus 1 equals secant squared theta. So that's an identity that is relating these things. If I could turn the secant x plus 1 equals tan x into something that had squares in it, then I would be able to use this identity to either make the tangent turn into a secant or make the secant turn into a tangent. So that's going to be my first strategy. I'm going to come over here, and I'm actually going to square both sides, which we're allowed to do because we're working on both sides of an equal sign. So we're allowed to do this. Okay. So to kind of summarize why I'm squaring, I basically didn't recognize any nice identities that were going to help me out to get the same trig function. So I want them to be like all sine or all cosine, all tangents, all secants, all cosecants, etc., etc., etc. So I'm going to try squaring it. Now, we got to be careful over here. We're going to have to FOIL. So I'm going to get secant squared x, and then I'm going to do the OI of FOIL is going to end up giving me 2 secant x, and then the L is going to give me a 1. And then over here, this side's easy. It's just tan squared x. So when I'm looking at this now, I still have multiple different trig functions, right? I have a secant squared, a secant, and a tan squared. And I really want them all to be the same. So I'm going to try to use this identity, and I have to pick. Do I want to try to change the secant squared into a tan squared plus 1? Or do I maybe want to work with this and say, hey, tan squared is going to equal secant squared minus 1? And that's actually the one I'm going to use because of this right here. I have a lone secant. So if I tried to turn the secant squared into the tan squared plus 1, I'm still going to have this secant here. So I'm still going to have multiple different trig functions, and I don't want that. So I'm going to choose very purposely to change the tan squared x into a secant squared x minus 1 using those identities, because now I have all secants. So I have all of one type of trig function. And now it's going to be much easier for us to factor and solve things. So I'm going to move things to one side of the equation and kind of see what happens. So first thing I notice is that the secant squareds are literally going to cancel each other out. Okay, as I try to move them to one side, they're going to be gone. So now I'm left with a 2 secant x plus 1 equals negative 1. I'm going to subtract that 1 over. So 2 secant x, I don't know why I can't write that c today, equals negative 2, which is going to give me secant x equals negative 1. And then, just like before, we don't really love working with secant, cosecant, or cotangent if we can avoid it. So I'm going to say, hey, if secant x equals negative 1, then cosine x is going to equal the reciprocal of that, so the flip of that. And the flip of negative 1 is still negative 1. So now I'm going to figure out, when does cosine equal negative 1? Okay, so cosine is x values, and the x values are going to equal negative 1 when I'm over here. So I'm going to get an answer that is x equals pi, and that's going to be the first thing we do. But we have to think about some other things here, which is a little annoying, but it happens sometimes. So first I'm just going to check against my domain. Pi is not in my domain restrictions, so I'm not going to stress about that too much. But if we go all the way back to our solving techniques from way back in the beginning of the school year, whenever we squared both sides, we instantly had to check our answers to see if they worked, because occasionally when you're squaring both sides, you can end up with an extraneous solution where you get a solution that works only when it's squared, but when they're not squared, you could get something like a negative 1 equals positive 1. And if those were squared, the negative 1 would turn into a positive 1 and it would work out. But since the original is not squared, we just have to check it. So unfortunately, we have to do like a true check here. So I'm going to do secant pi plus 1 equals tangent pi. And then I have to think about what's going on here. So secant of pi. All right, so pi we know is way over here, and we know that it's at a point -1, 0. Secant is really 1 over cosine, which means this is going to be a 1 over x value. Okay, and our x value is -1. So that's going to end up being -1 when we evaluate it. And then I have that +1 here, so the left side of the equation going to equal 0. So now we're going to focus on tangent. Tangent, we know, is y over x. So when I'm at this point over here, that's going to give me 0 over -1. And the last time I checked, 0 over -1 is 0. So when we were checking whether or not these things were equal or not, we got that they are. And so then we can confirm that pi is, in fact, the solution to this equation. Okay? So just to kind of summarize what we did in this one, because it's a little different from the other ones. It's not straightforward. There was no immediate way for us to get them to be all one trig function, so we wanted to try to do some math to figure out how to do that. And what I recognized was that there's an identity that involves secants and tangents immediately, and so I needed to square both sides in order to be able to use that identity. Once I did that, I was able to make them all one trig function, solve and get my answer. I got to be super careful because when you square both sides, you can get extraneous solutions. So I'm going to double check my answer. And then, of course, for all of this, I have to check what the domain is and make sure that I'm not violating that. All right, now we get to the last one. And this one's a two-parter that's going to be a little bit annoying for you. Again, kind of apologize in advance. But this all solutions is now different because before we were solving between 0 and 2 pi. And now we want every possible solution. So we're going to have to deal with that in a little bit. But let's deal with the first part, which is that we're going to use a calculator and we need to evaluate this problem here. And we know that we can use inverses to do that. So I'm going to do in the calculator cosine inverse of 0.7. My calculator is going to be in radians already. And when I do this, I'm going to get this answer, 0.7954, blah, 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 blah. All right, so I'm just going to write that down so I don't lose track of it. It was 795-ish. But let's think about this original thing here. So cosine x equaling a positive. We know that cosine is positive in quadrant 1, and then all students take classes also in quadrant 4. So we should have answers in both quadrants 1 and quadrant 4. And right now, the calculator only gave me this answer 0.7954, which I need to figure out what quadrant that's in. So what I'm going to do is just do the first boundary. So 90 degrees, which is going to be when I'm at the top of the positive y-axis, that's 1.57. So this 0.7954 is in fact going to be in quadrant 1, and it's that right there. So this is 0.795. And then I need to essentially use reference angles to figure out what this one would be. Now, cosine's kind of an easier one because we can just use negative angles here. We can say, hey, a negative 0.795, well, that's going to be an answer in quadrant 4. The other way we could do it if we really, really wanted to is we would have to think about what's happening here. It would be 2 pi minus that reference angle when we're in quadrant 4. So we would have to do 2 pi minus 0.795 in the calculator. We're going to get some decimal. I have no idea what it is because I didn't actually do that. So these are going to be our two answers between 0 and 2 pi. So, all right, so as I just said that, I realized that we didn't actually solve it between 0 and 2 pi, did I? Because I used a negative angle. So if I had done this, then I would have gotten answers between 0 and 2 pi. Okay, let's pretend like that was something that maybe we did, but this is all different because we're doing all anyway. So everything changes when we're finding all solutions. I'm going to start with just a positive one so that it's not as confusing for you. So that's my answer in quadrant 1, okay? But because it finds all solutions, that means that every single coterminal angle to this angle right here is also going to be a solution. So if I were to go all the way around the circle again, that's also going to work. And I could go all the way around in the opposite direction. So I'm going to do plus or minus and then a full time around the circle. And then you can use either the letter N or the letter K. And what this does is this captures all solutions if it lets me write that work for the positive angle. And then I need to repeat it for the negative angle, because that negative 7.95, that wouldn't be captured by adding 2 pi over and over. So I need to include both sets of angles and do both of them with a 2 pi k. And so this is going to be my final answer here. So essentially what you do is you find your answer like normal, okay? So just figure out what the answers are, just like we did in questions 3, 4, and 5. And then we're essentially just going to add a plus or minus 2 pi k. And there's some nuances there that we could talk about later, but we're not going to do that in this lesson. And just to kind of cement home what's going on here, let me get this. If I were to have done the positive one, I would have done 2 pi minus that angle. This would have been my second positive angle. So if I wanted to, I could have used, instead of this this negative one here, I could have used whatever that number was. I literally forgot it already. 5.488, 5.488. And the 0.795 and the 5.488, those would be our two answers between 0 and 2 pi. So if we'd solved like normal, that's what we would have gotten. And then I could have just added the 2 pi k to this one, okay? So essentially when you're finding all solutions, you're just going to solve it like normal, and then you just tack on this plus or minus 2 pi k for now. We'll talk about fancier ones in the future. All right, you should try to do the practice here. Okay, so you can see for like 1a and b, you're just going to be able to factor because they're already the same trig function. Same thing with c and d. Just try factoring, see what happens. And then for question 2a, you can see I gave you a little hint here. These are different trig values, so we don't like that. So if we use the Pythagorean identities, we can either turn the sine squared into a cosine squared somehow, some way, or we could turn the cosine squared into a sine squared somehow, some way. Here, they're different trig functions, so we could think about identities. I would honestly try multiplying first and turn everything into sine and cosine and see if things are going to work. And as I literally just said that's literally not what you should do. My bad. It's already factored. Just set each factor equal to 0. So you're going to have cosecant equals 2, and you're going to have cotangent equals -1. Just solve like normal. C is going to be where you want them to all be the same. And if I'm looking at this, I see a regular cosine. So I want to turn the sine squared into a cosine squared somehow, some way, using the Pythagorean identities. Here you can try practicing with the calculator. Just a note of caution with these ones. So we have to think about things. For this, sine is positive. It's going to give you answers in quadrants 1 and 2, but your calculator is only ever going to spit out answers for sine inverse in these two quadrants. You're going to learn more about that next year, so I'm not going to go into why that happens, but just know that you're going to have to do a little bit of math to figure out what the second answer is. Cosine, we already kind of did. We know that it's going to be in quadrants 1 and 2. Technically, cosine inverse will only ever give you answers in those two quadrants. Again, I'm not going to get into that. That's a next year thing for you. But you have to do a little bit of math to figure out what's going on. Tangent, it's a follower. It follows what sine does. Inverse in your calculator will only ever give you answers there. But if tangent positive, we know that that could be here or here. So again, we're going to have to do a little bit of math to figure things out. And for this last one, we don't ever do math with cosecant, especially in the calculator. So we would turn this into sine theta. I mean, it's 1 over 1.5. If you're using your brain, that's going to be 2/3. And then we're going to have that same idea. It's positive, so we're going to be in quadrants 1 and 2, but the calculator is only ever going to give you answers in 1 and 4 for sine inverse. So you might have to do a little bit of math. So we'll talk more about the calculator issues later, and I'll tell you what's important for you to know or not know. But for now, let's just assume it's always going to give you an answer in quadrant 1, and you might have to do math to figure out what it is in a different quadrant. So give that a try, see how it goes, and I'll catch you in the next one. Bye!